Welcome everybody to the inaugural Minerva lecture, and that's given by the eminent Professor Jean-Pierre Serre of the Collège de France. And these Minerva lectures were made possible by the generosity of the Fernholz Foundation that was created by Drs. Louisa and Robert Fernholz. And we're very lucky that Drs. Louisa and Robert Fernholz are able to attend today's lecture. So thank you for endowing this meeting. So I'd like to thank everyone here for the good humor in moving from the smaller lecture hall to this one. So it's my pleasure now to recognize Professor Manjul Bhargava, who organized these lectures. And Professor Bhargava will now introduce Professor Serre.
Okay, so I'd like to join Dave again and thank you again Fernholz and Fernholz Foundation for defense support in instituting and inaugurating these Minerva Distinguished Lecture Series in mathematics. The purpose of these Minerva lectures is to invite a distinguished professor annually for a period of about 2 weeks to deliver 3 accessible lectures to the members of the department on the topics of current interest. And what better way to inaugurate these lectures than with our speaker today, Professor Jean-Pierre Serre. Professor Serre has been an inspiration to scores of people in this room, including myself. He's made seminal contributions to mathematical research in diverse areas: topology, several complex variables, algebraic geometry, number theory. He's the recipient of the subject's most prestigious prizes, but I don't want to list them here. One reason being that they take up the whole hour. So Professor Serre's contributions to research are common knowledge, but what is perhaps slightly less known is his commitment to disseminating mathematics and making mathematics accessible to graduate students and to the general mathematical public. His writings and books continue to be used in our department as basic readings for our courses. And as you'll see today, in his lectures, he works magic with his chalk and his blackboard. When we first asked Professor Serre to deliver these Minerva lectures, he responded, "I very much like this proposal. The idea of asking for accessible lectures is what I like most. I shall be happy to come." And we're very happy to have him. Professor Serre's first visit was back in 1952, and it's a pleasure to have him back here with the auspices of these lectures. The title of his first lecture is Equidistribution. Please join me in welcoming from the Collège de France our first inaugural Minerva lecturer, Professor Jean-Pierre Serre.
Well, thank you very much, and thank you for Minerva Foundation. As Bhargava said, I found the idea of giving accessible lecture interesting and difficult. And I chose a topic, chose 3 different topics, but in fact related. I've been interested lately in the following game. You take equations with coefficients in the integer z. You reduce those equations modulo p. So they have a finite number of solutions which depends on p, and of course depend on the system of equations, let's say x. And how does that thing varies with p? You make p go to infinity. So that will be essentially the topic of the 3rd lecture. But when you study such questions, you find that you have to borrow mathematics from other fields, from analysis, analytic number theory, for instance, but more than that, algebraic geometry, of course. And also group theory, and that would be the topic of the 2nd lecture. So I thought I would divide the preliminary parts into two pieces, today which will be mostly analysis, but on, with arithmetic applications, and Monday it will be on linear algebraic groups. And the day after that it will be this, and x of p. So I will start with equidistribution. Very roughly, we will have to be more precise than that. We have some space x, and we have a sequence of points, x1, x2, xn. And we want to make precise. The idea is that those points are more or less at not at random, but they almost regularly distributed in x. So the precise setting that I will choose will be the following. I will take for x a compact metric. This is just because I want to speak the language of sequences, and it's only very good for metric space. And I will have a sequence of points in x. And the next thing that you will need will be the notion of a measure. I will need a measure mu on x. Now, measure theory and integration theory are essentially the same. You see, in integration, you want to integrate, you want to give a meaning to things like sum fx mu of x, where mu is a measure. But if you restrict yourself to a function f, which is a characteristic function, which is 0 somewhere and 1 somewhere else, characteristic function of some set A, then integrating the characteristic function is the same as defining the measure of A. If I call phi A as usual, this phi A of x, mu of x. And so measure and integration can be defined, and theory can be explained in either measure theoretic language or function theoretic language. But they are not exactly the same. And for some topics, it is better to take the function point of view. Despite the fact that in practically all the lectures, all the courses in the United States, I think the point of view of measure is the one people start with. But that is not convenient for me here. So here I will take the function point of view. That is, I will consider the space C of x of continuous functions on x with real values, but sometimes one has to use complex values too, real values. And the measure, by definition, will be a map. Well, I will be interested in positive measures and also of total mass 1. So from that point of view, this is just a linear map. It's a linear map, R linear, and so it maps a function f into something which, my God, is denoted by any number of notation. I mean, mu f would be possible, mu of f is possible. You also find sum x in x, f of x, mu of x. And you also find sum f of x, d mu of x, which I hate. I will explain why. Because it's contradictory notation. So a measure, a positive measure, is a function with only very simple axioms. It is called a positive measure I'm using positive in the sense I was educated with, that is positive or 0. It is a positive measure in the sense that f, so that's the first axiom, f of x positive for all x implies the integral mu of f is also positive. And the second axiom, if I want total mass 1, I will ask that if f equals 1, then mu of f is 1. And that's all. That's a big contrast with measure theory from the point of view of measure, that the axioms are so simple. When you have those axioms, you know how to integrate continuous functions. And quite often, of course, you need more, but it's a standard procedure to get more. For instance, you certainly want to define the measure of an open set. So let's U be an open set, and let's call phi of U the characteristic function of it. Phi of U equals 1 on U 0 outside. And then you define mu of U as sub for 0 smaller than f smaller than phi U or mu of f, where f is taken inside, f is continuous. So in the drawing I was making before, you have U, you have this function here, phi U. You take something which is an f which is like that. And you take the maximum. Of course, you define the mu of a closed set by complements. If you need 2, and you do need 2, you can define a set of measure 0 by the following rule. Set A as measure 0 if and only if for every epsilon which is strictly positive, there exists U open with A contained in U and mu of U at most epsilon. You could also go on and define a set which is measurable. That would mean that for every epsilon you can put it in sandwich between an open and a closed, where the difference of measure is at most epsilon. So there is no difficulty to define those things. It's a little exercise to show that an infinite union of sets of measure 0 as measure 0 as it should. So this is what I will use for integration theory. So then, or maybe I should explain why I dislike so much the d mu notation. It's the following. Quite often, and in fact in what we will do in this third lecture, X will be a compact manifold, differentiable manifold. Say of some dimension n, and with an orientation. In that case, you can speak of differential forms of various degree, but the interesting degree for us is degree n. So let's take a differential form of degree n. Then, well, how do you write it? In terms of local coordinates, you write omega is some function phi, and then things like that. Now, because you have an orientation and a differential form, it's easy to deduce from that a measure, mu index omega, which usually is written just omega. So, for instance, here you would write the measure associated with that, you would write it just dx1, dxn. And then, with the notation I was using, then it makes good sense to write sum of fx omega x, because the measure is omega. On the other hand, in differential geometry, people don't do that. It's very strange what they do. They write it d omega of x. And that's really terrible, because d omega is 0, of course. But of course, they know that they should not use d omega equals 0 in that situation. But when you learn the topic, it is so... I don't want to do that. So, end of parenthesis. All right, now equidistribution in that language. How do you write? How do you define it? Well, you have to start with x and mu, a measure, which is positive and mass 1. By the way, there are measures which are not positive, but one proves the difference of two positive measures, so it's not a big restriction. Now you have a sequence of points x1, xn in x, and you say that they are mu equidistributed if, well, the simplest way to say it is that to write if for every f in C of x, the integral of fx mu x can be computed just knowing the value of f on those points. It is limit for n going to infinity of 1 over n, sum I is 1 to n, f of xi. Sorry, capital N. And usually I write little n here. So that is the definition. But it's more understandable if you think that you are really working in a Banach space. You have C of x is Banach space with the sup norm, and then it has a dual, continuous linear forms, and the measures may be viewed as elements of the dual because they are continuous. So mu may be viewed as an element of the dual of C of x. And on the dual of a Banach space, there are several natural topologies, but there is one which I don't want, which is a metric topology. You have a norm on the dual, but it's terribly strong. I want the weak topology, where in terms of sequences means that mu n, a sequence mu n tends to measure mu if and only if it does so for every f, mu n of f, for every f in C of x. So that's the so-called weak topology. And we can rewrite this thing here in terms of the weak topology because I should have given you an example, a very naive example of a measure, which is you choose a point x0, or let's say little x. So we choose. And you look at the map, f goes to f of x. It certainly has the properties 1 and 2 that have, they're still on the blackboard. So it's a measure, it's a so-called Dirac measure. Dirac measure at the point x. And now you recognize in the formula here, you recognize that what I've written here is exactly that 1 over n sum for n equals 1 to n of the Dirac at xn should go for the weak topology to the measure mu. That is just two different ways of saying the same thing. It's good to see in the space, in this dual, in this big Banner space, let's pretend that this is this big Banner space. By attaching to a point x the Dirac measure, you're embedding, in fact, x is embedded like that, the family of the delta x. And an arbitrary positive measure is just a barycenter of various points on this thing. Because I could also write the following formula. Mu equals integral for x in x. Well, one will have to give a meaning to the formula, but it is suggestive. That is, you put the mass mu on x, you take the barycenter, and the barycenter is mu. And so you can view measures like this. Now, that is the definition of equipartition from the point of view of functions. Traditionally, it is stated in terms of measures, so let's try to do that. So, the measure point of view. What you do is you take a subset A in X, a subset. It has a characteristic function phi A, characteristic function. And you would like that the formula here works with phi A, which is not continuous in general, instead of little f. So you would like that if A is good, if A is good, but I will have to define what goodness is. If A is good, then you want that. Now, what is this side? You're integrating the characteristic function with mu. That is a measure of A. Mu of A. You should be able to compute it by taking this limit, and this is what? Limit n tend to infinity of, well, let's put a 1 over n. So, something wrong with the notation? Already? No, lim first, sorry. It's lim comes first and then 1 over n. And then, in analytic number theory, people would write it sum of 1. You see, I mean, that's the analytic number theories enjoy that, to write sum of 1. But then, everything important is is below the sum f. So, the n, well, they would write it xn in A n at most A, capital N. That is, you count the points in A up to the index n, and you divide the number by capital N, and you want that at the limit you get that. And with the definition that we have given on measure, all you can do at first is to prove it when A is open and closed. Because then the characteristic function is continuous, which is excellent for people who do Galois groups, because the Galois groups are totally disconnected. They have plenty of open and closed sets. If you know their measure, you okay. You need more than that. So the goodness in general is the following. So good means you take the boundary of A. I'm not sure people know what the boundary is, but let's pretend they know that it is the closure of A minus the interior of A. And it is a closed set. And you want that the measure of that, so good means that mu of the boundary of A is 0. And practically, it is necessary and sufficient. I mean, if you have an A which is not like that, you can make up some sequence which is, well, this is wrong. And so you have to know the boundary. For instance, many people believe, or seem to believe, that if you're working, if X is an interval, say 0, 1, you can define equidistribution in terms of sub-intervals. Open, see. Well, no, that's not correct. It's not true, except if the points of the boundary of the interval have a mass, which is strictly positive, then the equidistribution does not apply to the interval because you could not distinguish points inside and points outside. So one has to be rather careful. But that condition, boundary as measure 0, is called also quarable. At least in French, quarable. I'm not sure in English there is a word for that. Is it the same word in English? Hmm? Comment?
It's questionable.
Quest? Okay, okay. But in any case, this is what is. The trouble with that is that you have to know the measure in advance to know what are the quarable sets. And so it's practically impossible to define equidistribution without telling what mu is at first. Mu equidistributed is easy to define from measure theory, but not equidistributed for some mu. Because the only sets which are quarable for every mu are open and closed. That's an exercise. So, okay, so this is what quarable is. And I don't think I will give much more because I don't want to give a course in integration here. So let's go rather to the interesting examples of equidistribution. So the first classical example is the following. You take in the plane, in the complex plane, you take the circle of radius 1, and that would be x, the boundary.
Thank you.
Ah. So I hope this is clear. Take a circle in the plane and take the boundary. And you put on it the obvious measure. That is, if you represent by an angle phi, then you take the measure 1 over 2 pi d phi. So that it's invariant by rotation, and the mass is 1. Okay. Now, this is x. Now I have to give you the sequence of points, and you do the following. You take your circle, and you choose a point. Z. There. And you look at the iterate, not the powers. You look at the sequence, say z, z square, z cube, z n. It may be that z is of finite order. In that case, after some number of steps, you go down, you go back to, you go to 1. So you assume not. You assume z as infinite order. And the really first basic example of equidistribution is that then those powers are equidistributed. Then the n are mu equidistributed. And it is worth explaining a little the proof, because the idea is used in many other case, less elementary. The first idea is that those linear forms given by measures on this Banach space are, so to speak, equicontinuous. They have norm at most 1. And so you can, that's very easy for going to the limit. So in particular, to prove that a sequence xn in X is mu equidistributed, you do not need to check it for every f in C of X. It is enough to check it on some sequence fi such that their linear combinations are dense. So for instance, if X is in R, you can take just the powers of the variables. Powers. If you check the convergence for those, you win. So if you know that, then the way you prove this thing is that you take for f, well, you take the z goes to z to the k, where k is z. And the linear combinations of those are dense, of course. So you have to check something, oh, sorry for the z, that's not a very nice notation. So where x is any point x in the circle x. And you have to show the convergence for every k. So let's do it for k equals 1. In fact, when you have done it for 1, it implies the others. So for 1, what does that mean? It means that you have to compute the limit of 1 over n sum n of, well, z to the n. And that should be the same as for the R measure, the invariant measure, which is 0. You should find 0. But what do you find actually? Because, well, you find 1 over n, z minus z n plus 1 over 1 minus z. And this is at most 2 over n, absolute value of 1 minus z. And so these things are fixed, but n goes to infinity, so that goes to 0. And the proof for an arbitrary k is the same. So that's a famous argument of Hermann Weyl. In most books and in Hermann Weyl, you find it written in a slightly different way, because instead of the circle in the plane, one takes R over Z, and then it is the so-called N alpha theorem. If you want a slightly more general statement, here it is, here is one. You take for compact space a group G, compact, a commutative V group, and you take a Z in G with the property that the powers of Z are dense. Then it is equidistributed. Then Z, Zn are mu equidistributed, where now mu is a R measure. And for the proof, you have a choice. You can either redo the previous proof, but using the characters, the continuous characters or you can deduce it from the case of the circle. So it's really not an interesting generalization. So this is essentially the basic example that you find everywhere. So I will be interested in other type of examples where the index set will not be now the integers. The index set will be the prime numbers. So I'll be interested in sequences xp indexed by primes. But of course, that's amount to the same, except that I have to say how I order the prime, and I order the prime by the size. So the prime ordered by size. Well, it's obviously the thing to do here, but you have to realize that sometimes you don't have a natural indexing of an infinite set. For instance, if you're interested in number fields, then you want to take for index the set of prime ideals. And if P is such an ideal, the norm of P should be increasing. So what you want to do in that case is to take the set of prime ideals and put on it a total order in such a way that if norm of P is bigger than P prime, then P in the order you have chosen is bigger than P prime. But if you have several, no, can you help again? This is not a stable situation.
There we go. There's a clip.
Okay. But if you have several primes of the same norm, it doesn't matter. You put them in the order you choose. The point is that when you have a sequence which is equidistributed, you're free to change slightly the order of the terms. If you change in such a way that the nth term in one goes to n plus little o of n, you don't change them too much, then it works. And this is where the difference between number fields and function fields is very serious, because for function fields you cannot do that. For function fields there are too many primes of the same order. So there is no way, no reasonable way to order them. So in that case, what you do is you put them together. You just make the sum of them. But I wanted to explain that. Okay, so let's go to examples with primes. Well, some examples, I will divide the examples in two categories: motivated examples and, well, I don't want to be rude with the other one, so instead of unmotivated, let's say not yet motivated. Well, for instance, you have heard of the Sato-Tate conjecture, which has been proved in very special cases. Beautiful, but very special. And the general case is well motivated in the sense that if we only had the full dictionary between motives and Langland's theory, and the full Langland's theory also, if we had both these little things, then the Roche-Tate follows immediately. So it is motivated in that sense. And here I'm using motive also in the sense of Grothendieck. But there are some very interesting equidistributions which are not motivated. So let me give you examples of both. And I'm not going to tell you which I consider as more interesting than the others. I mean, that's the, they are both extremely interesting. So an example due to Hecke, a very ancient one. Let me explain it only in the case of Z of I. And the set of indices will be not all the primes, but the primes P congruent to 1 mod 4, ordered by size. And each such prime can be written as a norm of some A plus BI. That's right, norm of pi, that is A squared plus B squared, for some A and B. And there is almost unicity. Well, it's not really unique. There are 8 possibilities because you can change the sign of A and B independently, and you can permute the role of A and B. So that's 8 cases. But more importantly, I'm going to write A plus BI. So it's a point in the plane. And what we want is the angle. So as I said, it's not really well defined, up to 8 possibilities. So you write it as P1/2 phi. And you want the equidistribution of phi. And that it is true, well, after a little, for instance, one possibility is to take P to the 4 instead, because then you kill at least 4 of the ambiguities. Then there is only a complex conjugation, but not important. But Hecke proved that these are equidistributed. That is, if you look at the prime elements of the Gauss integers, and you look at them, the angles are really equidistributed, and this is proved in a very nice way by using analytic functions. But I don't think I'm going to describe that point of view. But there is a general philosophy in analytic number theory that if you can make L functions with suitable definitions, and if they behave well on the line 1, holomorphic and non-zero, then you can deduce from that equidistribution by taking a logarithmic derivative and so on. So this is an example of a perfectly motivated equidistribution, not trivial at all. Hecke proved it, in fact, for every number field. But for other number fields, you have to be more careful because, as you can see here, the units give you trouble. You could multiply by units. If the field is a real field, then you cannot do that. But the circle is replaced by a hyperbola in the case of a real field, and then you have a group of translation on hyperbola, and you work modulo that group. But this was done by Hecke in around 1910, I don't remember. So, okay, 100 years ago. So, let me give you a motivated example. There is one which is due to, now let me try to remember, there are 4 people. Duke, now Ivanets, you're going to help me. Ivanets. What are the people I want to quote? Toth and Friedlander. It's a paper in the Annals. It's about the following game. You take a quadratic equation. You could take x squared plus 1 is 0. That would be just as interesting. So take that one. And you take a p for which this has a solution. So p congruent to 1 modulo 4. So that you know that you can find such an x in Z. mod P, well-defined up to sign. And you can, as every number here, you can represent it by a number, in fact, it is non-zero, so you represent it by a number between 1 and P minus 1. And since there are two possibilities, you can do even better, you can do that. And so you get a point x index P. It is not in a fixed interval because this goes, the size goes to infinity, but you normalize it. And so finally you get a point xp divided by, well, let's divide it by p minus 1 over 2. So then it will be between 0 and 1. And you have a point which depends on p, and now you can guess the theorem that they prove. They prove that these things are equidistributed for the standard measure on 0, 1, for the measure dx on 0. What is? Yeah, then I would be interested to in fact, I was going to discuss that, you see. I was going to, let me say what I wanted to say, and then you explain to me what I missed. I wanted to say that, is it surprising? Well, yes, what is surprising is that it can be proved. Because it looks something really impossible when it can be proved. But that it is true, naively one would think, yes, maybe. But why would you think that? Well, it seems that Sarnak has some reason to believe that. I don't really have a good argument. On the other hand, when I was told that, I said, of course, they are to be equidistributed because they are at random. And that's a terrible argument. And okay, so Sarnak, I will ask you a bit later. I want to explain something else about randomness now. Long ago, maybe I was a graduate student, I'm not sure, but I was very impressed by the following theorem. Almost all sequences on 0, 1 are equidistributed with respect to the standard measure for mu equals dx. So my first reaction was, oh my God, so the measure on 0, 1, the Lebesgue measure is so remarkable that almost everything is equidistributed. But I was also a little bit a topologist at the time, so I knew that if I do that, this is also a segment 0, 1. So if that statement was really correct, that would mean a measure of that invariant by homeomorphism. That doesn't exist. So the statement is tricky. That is, it should say mu almost sequences are equidistributed. That is, what is a sequence after all? It's a point in x cross x cross x. And that's an infinite product of copies. It's compact, metric. And also, when you have a measure mu on x, there is a standard way to make an infinite tensor product. It's very simple to define. From the function point of view, you take the functions which depend only on finitely many entries. And so, a sequence is a point here. And what the statement says is that if you put on that the product measure, then with that measure on x infinity, you have that. it would work exactly the same way if you put a stupid measure like the Dirac measure, for instance. You could do that. And so that is not an argument for guessing that in this theorem it is a standard measure. Now, Sarnak, I'd be interested to know what. No? It's a bit too long?
I'll show you after.
Okay. What is surprising in this is that you're doing a curious game. The curious game is here. That is, you're taking representatives from an integer mode P inside the integers, inside the real numbers. And you could do something analogous periodically or eladically. To say it in an elementary way, let's say the following. Let's make a variant of this theorem where I take the same xp and I reduce it modulo something. So let's take an example. I take xp and I reduce it mod 7. And now I have a family of points, let's call them xp7. You have a family of points in a finite set. Are they equidistributed for the obvious measure here, where you put mass 1 over 7 at this point? And I asked Kowalski about that. He made some experiments because that's very easy to do on a machine. And the experiments essentially worked. But it's an open question. So so that is open. It should not be much simpler than what Ivanets and the rest did in general. It should not be something easy.
What is your choice of XP? After the normalization is between one, I mean your XP, because doing mod 7, if XP is only modulo P, then it makes no.
No, I'm reducing XP. XP is just an integer. It's an integer between 1 and P minus 1 over 2. I reduce it mod 7. And then I ask whether that is random. That is. Let me also mention some unmotivated, conjectural example. Because they are unmotivated, there is no obvious way to attack them. That is why they are a bit harder. So it's an example of the so-called Klosterman sums. Or maybe cats will consider they are motivated. I'm not sure. Maybe. For myself, no, they are not motivated. So what are the... let me say it brutally. You do the following. Judging what one wants to prove. I will not formulate it in terms of equidistribution, but I will just write some sums. So you take a prime P, and you consider a sum like sum of, I have to be careful, cosine. So I'm going to make a sum Zp equals, and then I divide by square root of P. There will be more here. And x mod P cosine x non-zero mod P of say x plus lambda x minus 1. X minus 1 has a meaning mod P because I have put that. So for every P, you can compute that, you fix a lambda. Fix lambda, for instance, lambda equals 1. It's unknown in that case. And those things are known by a theorem of Weil, André Weil, to be between -2 and +2. And the conjecture is that these things, well, the experimental evidence is rather strong, that they are equidistributed on this interval, but for the so-called Sato-Tate measure. Equidistributed, so conjecture. I don't think one can attribute the conjecture to anybody precisely. I think I thought about that long ago, and you certainly must have thought about it, but since we didn't see any way to attack it, we didn't publicize it. So conjecture that these ZP are equidistributed with respect to the Sato-Tate measure. On the interval -2 +2. Now, Sato-Tate measure, it's better that I write a formula for it. It is a measure which has a density with respect to the standard measure. It has a density phi of x dx, where phi of x is a constant times square root of 4 minus x squared. You see x is in between -2 and +2, so that is nicely positive. And the constant is such that, I don't remember the constant, there is a 2 pi or 1 over 2 pi. The constant should be such that the total mass should be 1. So that is a Sato-Tate, but that is a bit not very bright definition of it. I have 2 minutes left. Good. The intelligent definition is the following. You take the compact group SU2C. The elements are the 2 by 2 matrices which are unitary of determinant 1. And you look at the trace. And this maps the group on -2 +2, the unit element gives you +2, the -1 gives you -2. Now you take the Haar measure here, normalized by the total mass 1, and you take the image, because there is a very simple notion of the image of a measure. In the language of integration, it's pseudo-trivial, and that is a Sato-Tate. Comment?
Was introduced way before Sato-Tate. Wigner. In studying atoms.
Okay, but the Haar measure was there before, so it's difficult to say. But it's a case where the density is quite nice, because if you rewrite this formula correctly, you will see that if you take, you don't have to, on this axis, you have to make a homotopy, but then the density gives you a circle, a half circle. Okay, so this has been checked numerically. It's very easy to check. I don't have enough time to explain how you check those things. But let me just say that you check them indeed from the definition with f. But you choose good f's. You choose, for instance, monomials. So that is the old point of view on measure on the line to take the moments. Okay, but I think I'm going to stop here.
Okay, well, thank you so much. Any further questions for Professor Serre?
Allez, Sarnak, tell me why it's motivated.
So, to be honest, the first thing I said was you can't do it, and he proved me wrong. So I ended my book by saying this is too difficult, and it's beyond the methods that exist.
Oh yeah, but you never say that. I know that.
So that was the first mistake.
Yeah.
But I actually explain it in terms of something called a Salier sum. I show that you equidistribute it on the integers, and I said, I don't see how to sieve to primes. So it's very close to your Klosterman sum with a twist. So I would say, I don't know about motivators, I don't know what.
I cannot define it, of course, precisely, but I mean that in most cases here, you see, well, in the motivated case, the equidistribution is a byproduct. That is not the main theorem. The main theorem is that the thing is a motive, or that the L function extends as a functional equation, and so on. In the unmotivated examples, we see no L functions, and and then the theorem becomes its own, so to speak. It's not a corollary. It is a theorem.
Would you consider the Riemann hypothesis to be unmotivated?
What? Agent provocateur, one says in French. No, but I wanted to make a distinction between the things which would follow when, as soon as we get Langlands plus the motive, so that's soon enough. Hopefully.
Any other questions? Okay, well, let's thank the speaker again.